the first thing we need to talk about here is that you've got your structure of ethanol and you've got your structure of butanol. And the peak absorption for ethanol was at 290 nanometers. I don't know if you saw that. And for butanol was at 330 nanometers. So my question is, well, first of all, which one of these required more energy? Yeah, so a lower wavelength is higher energy. So the two ethanol required more energy for the transition. And then the next question is, what transition required that energy? Where did that energy go? Yeah, so it's electronic spectroscopy, and the most intense one is normally HOMO to LUMO. But what are the HOMO and LUMO for these molecules? It's the same for both of them.
Pi to pi star.
Yeah, close. So if we look at this carbonyl bond, we've got the carbon and the oxygen p orbitals, and they'll form a bonding and an anti-bonding combination, pi star and pi. But this isn't our HOMO. Can anyone think of what might be higher in energy than our pi? Sigma star. Well, we don't have any electrons in there. What's floating around our oxygen?
Non-bonding.
Yeah, so we've got non-bonding oxygen orbitals, which are populated with electrons in our HOMOs. So the transition that we're looking at, I'm just going to draw it in pink, is this transition here from our non-bonding pair to our pi star. So what would either, to reduce that for butanol, we either need to raise the energy of our lone pairs or reduce the energy of our pi star. What do we think is happening?
Increase the energy of non-bonding.
Why would we increase the energy of the non-bonding pairs here?
Oh, no. Decrease the energy of pi star.
Yeah, I think that seems a bit more likely, doesn't it? What's doing that?
System.
CC double bond.
Yeah, so somebody said conjugated system, somebody else said CC double bond. It's this, isn't it? So I don't know if you remember organic chemistry, you can do Michael addition onto that carbon and do something like that. You get these resonance forms, and that's happening throughout. But the resonance forms actually don't explain why you've lowered the pi star orbital. There's no molecular orbital theory in this conjugated model. There's no immediate answer why having a negative oxygen would lower the pi star orbital. And so to look at that, we're going to look a bit closer at these molecular orbital diagrams. So this is a carbon-oxygen bond here. I'll put that on this side. That's our carbon-oxygen pi bond. And we've got another one now for the carbon-carbon. Our pi and our pi star. And in the middle here, we're going to have 4 molecular orbitals. Does anyone know how these are going to interact? What's the symmetry requirement for bonding? And can I form a bond between a pi and a pi star orbital? No, because every combination that I make will be non-bonding overall. So I have to bond the pi with the pi and the pi star with the pi star. So you end up with these 4 levels like this, where we've changed our HOMO up a little bit, and we've lowered our LUMO by this orange amount here. So we've lowered our pi star LUMO by bonding it basically to this C+1C, and that's a molecular orbital way of thinking about conjugation and ethene versus butadiene effectively, if this was a carbon on the end. So I'm just going to rub some of that out, and we can think about this maybe a bit more intuitively. So if we start off looking only at the p orbitals that are in our pi bonding framework here, and pretending that they're all in a line. This is something called Huckel theory, which you probably will come on to next semester, I think. What's the most bonding combination, right? What's this going to be?
All in phase.
All in phase, exactly. So we've got a carbon-carbon double bond and a carbon-oxygen double bond, and there's a bonding interaction between them. And what about this one here? Yeah, exactly. So you've got a carbon-carbon double bond and a carbon-oxygen double bond, but this time they're anti-bonding. So that's raised their energy relative to each other. So you've got a stabilized pair and a stabilized orbital and a destabilized orbital. And then the same thing happens for the anti-bonding combinations. So you've got a stabilized anti-bonding interaction where there's a bonding interaction between the carbonyl and the carbon-oxygen. And you've got a anti-bonding combination going across the whole set where you've got a completely anti-bonding set. So you can see now that either thinking about it this way or thinking about it this way, we've lowered the energy of our LUMO, and that's why this has a lower energy transition. Would anyone like me to go back over that? Because sometimes it's conceptually a bit far away from.
That makes sense to me. So.
Yes.
Okay, great. So the other important thing that we need to think about with this experiment is what absorbance actually is. So you've got your spectrum here with absorbance on this axis and a wavelength down here. You've got a nice lump in the middle, and it goes 0, 1, 2, 3, 4. What is that? What are we recording? So if we've got our sample vial here and we fill it with some solution, or in our iodine experiment you saw it was a big tube and it was full of gas, doesn't really matter. We shine some light on it with a specific wavelength, and that has a specific intensity. And then it goes through our sample and we get slightly less light back out the other side. And I'm going to call that IC for light collected. Some people just call it I. Some people call it IR for light received, intensity received. But I'm going to go intensity collected. And how does this intensity collected relate to our absorbance? There's nothing really about energy here. It's more about how much light goes through. So it's a lot like the pH scale, because it's logarithmic. I think that could be slightly too involved. All I really want is this logarithmic scale here. So we report UV-Vis spectra on a logarithmic axis. So for an absorbance of 0, how much light is being collected? What's IC?
All of it.
Yeah, so we're getting 100%. So our ratio of I0, the collected light over the initial light, we're getting 100% of it back when there's no absorbance. What about an absorbance of 1? So if this side of the equation is 1, we've got IC over I0 equals 10 to the minus 1. If you take this minus sign over and then put both sides to the power 10 to the power of both sides, you get this. What's 10 to the power of minus 1?
0.1.
Yeah, or 10%. What about 2? So this time we 10 to the minus 2.
So 0.01.
Yeah, or 1%. And then 3.
0.001. So 0.1%.
0.1, isn't it? 0.01. And then 4 is then 0.01%. So the sensitivity of our detector isn't very good above 2. So we normally say that if your UV spectrum goes above 2, then it's useless above that point, because our detector can only detect percentage differences. It's not sensitive to 0.1, and it's certainly not sensitive to 0.01% differences. So this is important for question 9 of your post-lab questions. And a good answer to that question will include some reference to this relationship of light collected over light emitted and the sensitivity of our experiment. Okay, so that was a nice aside about theory.